Okay, so in this lecture, we prove the first part of the cyclic decomposition theorem. Cyclic decomposition theorem. Okay, okay. So the cyclic decomposition theorem is actually it has actually a very big proof. So we proved the first part of the cyclic decomposition theorem, which specifically deals with constructing some certain tools which can be then readily applied to show that the cyclic decomposition theorem holds. And there is a certain statement regarding uniqueness of the cyclic decomposition theorem. So that uniqueness part, we are also going to keep that for the next lecture. So what have we actually done is that the cyclic decomposition theorem is broken down into four specific steps. We are going to prove the step 1 and step 2 in this lecture, and we are going to prove the step 3 and step 4 in the last lecture, in the next lecture. Okay, let's first start with the statement. One thing more to be said is that the conceptual part of the cyclic decomposition theorem will be understood better if you have already viewed the previous 3 to 4 lectures, starting from cyclic subspaces. Okay, cyclic subspaces and T annihilators. Starting from that very lecture, these lectures are available in this playlist as well. So there are, I guess, 3 lectures or 3 to 4 lectures before this lecture, starting from the lecture on cyclic subspaces. So just view those 3 to 4 lectures, and then you will be ready to understand the cyclic decomposition theorem. Otherwise, it will be a bit more complicated to understand this. Okay, because throughout those 3 to 4 lectures, we have conceptually built uh, some more important aspects which we will be readily using in this cyclic decomposition theorem. Okay, so what is the theorem of it? Let T be a linear operator on a finite dimensional vector space V, and W naught be a proper T admissible subspace of V. A proper T admissible subspace of V. Okay. Then there exists non-zero vectors, which are alpha 1, alpha 2 till say alpha r. Obviously, all are in V with respective T annihilators, which we denote as P1, P2 till PR. That is, P1 is the T annihilator of alpha 1, P2 is the T annihilator of alpha 2, so on and so forth. PR is the T annihilator of alpha R. Such that, number 1, the vector space can be decomposed as follows. So W naught plus the T cyclic subspace generated by alpha 1, direct sum the T cyclic subspace generated by alpha 2, and so on till the T cyclic subspace generated by alpha R. And number 2 is that the kth T annihilator divides the k minus 1th T annihilator. This happens for all k is equals to 1 till r minus 1. Right? So 2 to r. Very sorry. The range, because we have the k minus 1th term, right? So it happens from 2 to r. 2, 3 till r. Yeah, correct. Right? So, furthermore, the integer r and the annihilators we have, the integer r Okay, and the annihilators P1 till PR, they are uniquely determined. They are uniquely determined by the statements 1 and 2, by 1, 2, and the fact that these alpha k these vectors alpha 1 till alpha r, they're non-zero. That no alpha k is 0, where k ranges from 1 to 1 to r. Okay. Okay. So let's prove this statement. Okay. So okay. So the proof, step 1. Okay. So what we are going to do in step 1 is that we will show that there exists non-zero vectors beta 1, beta 2 till beta r in V, such that V can be decomposed as somewhat given in the cyclic decomposition theorem. That is, we show that there exists non-zero vectors beta 1, beta 2 till beta r in V, such that number A, that V is decomposed as some W naught. W naught is a T admissible subspace, proper T admissible subspace of V, plus this T cyclic subspace generated by beta 1 uh, plus the T cyclic subspace generated by beta 2, and so on till the T cyclic subspace generated by beta r. Observe that we are not talking about direct sums here. The concept of direct sum will be readily included in step 1 once we reach step 3, and that will be the final aspect of the proof, which we're obviously not going to cover in this lecture. But we first need to discuss about the conceptual portions regarding direct sums first, to have a better understanding of what happens or what leads to this decomposition being a direct sum decomposition. Okay. So yeah, so T cyclic subspace generated by beta r, sorry, not B, T, right? And number B is that if we choose an index k uh, between 1 and r, and the subspace wk is given as w naught plus the T cyclic subspace generated by beta 1, and so on till the T cyclic subspace generated by beta k, then the T conductor of beta k, into wk minus 1, say, which we denoted as pk, and we have also used this notation in the previous lecture, small s beta k wk minus 1, has the maximum degree among all T conductors into the space wk minus 1, has the maximum degree of all T conductors into the space wk minus 1. Or we can mathematically write it like this, that is, for all k, degree of pk is the maximum of the degree of the T conductors of alpha into wk minus 1, where alpha ranges over all the vectors in V. Clear? So this is the degree, correct? Okay. Okay, so let's see the proof of it. Now, typically the proof only depends on the fact that W naught is T invariant. And W naught is clearly T invariant because W naught is T admissible. Okay. What we do is observe that suppose we choose a proper T invariant subspace of the vector space V. Let a W be a proper T invariant subspace of V. Then clearly the maximum possible degree of the T conductor of a vector alpha into W degree, this is greater than 0 and less than equal to V, right? Clear? Therefore, we can choose a vector beta such that this maximum is attained. Therefore, we can choose a vector beta from B such that degree of the T conductor of beta into W attains the maximum. Clear? If beta is that vector, then what can we say about this space W plus the T conductor of beta? Then this obviously has dimension larger than dimension of W, right? So it has dimension larger than dimension of W, and the space is also T invariant, and W plus Z beta T is T invariant. Clear? Okay, is this observation clear? So coming back to the proof, we simply apply this observation to W naught. Okay, because W naught is given to be a proper T admissible a subspace of V, so it's obviously a proper T invariant subspace of V. We apply the above observation to W naught. Okay, clear? So if we apply the above observation to W naught, then we will be getting a vector beta, which we denote as beta 1, let's say. To get beta 1 in V, then we have the subspace W naught plus the T cyclic subspace generated by beta 1, right? Now if this subspace is still a proper subspace of V, obviously it's T invariant from the observation, right? It's obviously T invariant. Its dimension is greater than dimension of W. So typically it's if it's proper, then we can reapply this observation to this subspace. Else this gives a decomposition of V, not a direct sum decomposition. It gives a decomposition of V, which abides the first statement of this step 1, right? So if this subspace is proper, then reapply the observation, right? Then reapply the observation to W naught plus the T cyclic subspace generated by W1, and then again we will get another vector to get some vector beta 2 in V. Now obviously these are non-zero vectors, right? By assumption, we have chosen this maximum degree to be something greater than 0. Clear? To get beta 2. Then consider the following subspace. Right. Consider the following subspace. So we already had W naught plus the T cyclic subspace generated by beta 1, and we add the cyclic subspace generated by beta 2 now, right? and the process continues, because again, if this is a proper, so this is again T invariant, right? So if it's a proper subspace of T, then we reapply the observation. So the continuing the process, continuing the process, continuing the process, what do we have? Okay, one more thing to observe here, we have not named these subspaces as given in the step 1. So this subspace is typically W1, okay, and this subspace is typically your W2, right? Is it clear? So we just keep on applying this process, or rather let me write it in this way, that since dimension of Wk, obviously Wk can be recursively defined in this form, right? So as, and that is also what is given in the statement of step 1. So if dimension of Wk is since dimension of Wk is greater than dimension of k minus 1, therefore we must reach some Wr which be equal to beta equal to v in not more than dimension v steps, right? Right? Is it clear? So the maximality condition is already included in this proof, right? And we have also gathered the subspaces W1, W2 till W0, W0 or W0, W1 till Wk. Or here, according to the step first statement is step 1, we have this to be W1, W2, and this is your WR, right? Okay. These subspaces will be required in the next step as well. So Wk will ideally have this sort of a structure. Clear? Okay. Now let us move on to the step 2. Okay. Step 2. What do we show in step 2? We show that let beta 1, beta 2 till beta r be non-zero vectors, be non-zero vectors which satisfy conditions A and B of step 1. Clear? We fix some k within the given index. Okay. Let beta be V and let F be the T conductor of beta into Wk minus 1. Okay, Wk minus 1, the structure is already clear from the previous from step 1. Wk minus 1 has that structure of step 1 only. Okay, Wk has this structure, so obviously Wk minus 1 will have the same structure till the T cyclic subspace generated by beta k minus 1. Okay, Wk minus 1. If Ft of beta is of this form, so it's beta naught plus summation 1 less than equals to I less than k, that is the summation from 1 to k minus 1 of some polynomial gi t beta I, where beta I is in Wi, beta naught is in W0, beta 1 is in W1, beta 2 is in W2, and so on and so forth. Beta I is in Wi. Then F will divide each of the polynomials gi, where gi is a polynomial, and we have one more statement that beta naught can be written as some f of it can be written as f of t of gamma naught, where gamma naught is an element from W naught. Clear? Okay, so let's see the proof of step 1. Step 2. Okay, now observe that the proof of step 2. What happens if k equal to 1? So if k equal to 1, we have nothing to say about this part. So ft of beta becomes beta naught, right? Beta naught in W naught. So that means, so since W naught is T admissible, and we have seen by the definition of T admissibility that if a vector of this form, ft beta is inside the T admissible subspace W naught, then there exists an element in W naught such that ft beta is equals to ft gamma naught. This implies there exists some gamma naught in W naught such that ft beta must be equals to ft gamma naught. Clear? And ft beta is beta naught nothing. So, right? So it's clear, right? So if k equal to 1, we only have the statement for the T admissibility of W naught, right? So it's a trivial statement. We are more concerned about when k is not equal to 1, and that's obvious, right? Therefore, let k be greater than 1. Okay. What we do? So we need to show some sort of a divisibility. So the obvious procedure we will be trying to follow is the division algorithm. Right? We apply division algorithm on gi, each of these gi's by f, to get polynomials hi and ri such that, right, so we have gi is equals to f times hi plus ri, where obviously the conditions implied on ri are that either ri is equals to 0 for all I, or degree of ri is strictly less than degree of f, right, for all I. Obviously we have I ranging till k minus 1, sorry, ranging till r minus 1, or what was I ranging from? I forgot the index. Yeah, so we had fixed a k. Yeah, I ranging from k, I ranging to k minus 1. Correct, correct. I ranging from 1 to k minus 1. Correct. Yeah, we are concerned about I ranging from 1 to k minus 1 because there is no sort of a existence of a polynomial gi in term of I equal to 0. Right? So I ranging from 1 to k minus 1. Correct. Okay. So obviously, to show that f divides gi, we need to show ri is equals to 0. To show that ri is equals to 0. Okay. One thing which I would want to do here is that I need to change how I write r, because I will be using the symbol gamma as well. Okay. So let me just write r as like this here. Okay. Yeah. Okay. So I need to show that ri is equals to 0. Clear? And obviously for all I. Let us use a vector gamma, which is beta minus summation over I is equals to 1 to k minus 1 hit beta I. Okay. Now each beta I is from wi, that is beta 1 is in w1, beta 2 is in w2. What was w1? W1 was T invariant, w2 was T invariant, w3 was T invariant. W1 was in the form, right? It was in the form w naught plus the T cyclic subspace generated by beta 1, and so on and so forth, right? So each w1, w2 till wk, or in fact wr, they are all T invariant subspaces. Each beta I is from wi. So hi of T beta I, this whole element is from wi, right? In fact, the sum is also in wi because the way wi was constructed, right? Clear? Okay. So this implies gamma minus beta this belongs to wk minus 1, right? Because what was wk minus 1? Wk minus 1 was of this form, right? This was w naught plus the T cyclic subspace generated by beta 1 and so on till the T cyclic subspace generated by beta k minus 1, right? So, so we choose an element beta 1 from here, let's say beta k minus 1 from here, sort of, right? We are not considering, suppose let's say 0 element from here, for example. Then we have h1 of t of this, hk minus 1 of t of this, we sum all of them, right? So this is obviously an element from wk. That is what I wanted to say. Clear? Okay. Okay. Let me drop this portion. Yeah. So the gamma minus beta is in wk minus 1, right? Clear? Okay. So if gamma minus beta is in wk minus 1, this this is from the observation which we had done in the previous class, the last observation we were talking about. This typically means that the T conductor of gamma into wk minus 1 is equal to the T conductor of beta into wk minus 1. Clear? And we choose this to be F. Okay. Clear? Okay. So furthermore, what we can say about the image of gamma under f of t. Okay. Furthermore, observe that what is f of t of gamma. So f of t of gamma by definition of gamma is f of t of beta minus summation over I is equals to 1 to k minus 1 f of t hi of t beta I, right? Okay. But f t hi of t can be written as g of t minus ri of t, because gi was written as f into hi plus ri, right? So this is f t of beta minus summation I is equals to 1 to k minus 1. This can be written as gi of t minus ri of t beta I, right? So this is basically equal to gt ft beta minus summation. I'm not writing the index anymore. So it's git of beta I plus summation I equals to 1 to k minus 1 rit of beta I. But what was ft of beta? What was ft of beta? So ft of beta was given in the statement, right? Beta was a certain vector it assumed for the statement. That ft of beta can be written as beta naught plus, so it can be written as beta can be written as, or we had the expression for ft of beta itself, right? We just see once. Okay. So we had ft of beta to be, okay. So we have ft of beta to be beta naught plus summation I is equals to 1 to k minus 1 git of beta, right? This is what we had. Clear? So we just put it here. We have minus gi of t beta I plus some summation of rit beta I. So this part cancels out. So we are left with beta naught plus summation I is equals to 1 to k minus 1. Sorry, let me just use the notation. Yeah, ri of t beta I. Okay. I don't want to confuse between r and gamma, because I readily got confused when I was writing this proof down. Okay. So yeah, r, yeah. Okay. Is it clear? Let so this is equals to ft of gamma, right? Okay. We number this statement to be 1. Clear? Now what we do is we simply choose or we simply assume that ri is not equal to 0. We want to prove ri is equal to 0, so obviously we we will reach some point of contradiction, which will obviously imply the fact that ri must be equal to 0. Okay. So let me move to the next page. Okay. Let ri be not equal to 0. Clear? We choose a largest index. Let j be the largest index We need to show that Ri is not equal to 0 for all I. So we choose some largest index j such that Rj is not equal to 0. That is our intended fact. So let j be the largest index such that Rj is not equal to 0. Okay. Then the expression of ft gamma, this can be readily written as beta naught plus. Now we are not intended to have this sum till k minus 1 because we have some index j. Beyond j, every Rj is 0. So we can just have this sum I is equals to 1 to j. Right? We have Ri of t beta. One more thing, I just say it here. Often I will write Rit or some f of t, some vector beta as f beta. I often misplace the the alphabet t, the symbol t in this case, in this representation. Okay. Okay. I guess this is clear. This part is clear. Okay. Where? So what was the condition implied on these polynomials Ri? Where either Rj is non-zero by assumption, and the degree of Rj is less than degree of f. This was straight away from the division algorithm, right? We choose the t conductor of the vector gamma into Wj minus 1. Let P be the t conductor of the vector gamma into Wj minus 1. Okay. Now obviously Wj minus 1 is contained in Wk minus 1 simply since j is less than k, less than equal to k to be very precise. Okay. Then f, which is the t conductor of say gamma into Wk minus 1, this must divide P, right? This is straight away from observations regarding T conductors. Okay, we have a completely dedicated lecture to T conductors and T annihilators, and we also, I guess, we also had discussed this divisibility property in the previous lecture as well. Okay, so F must divide P then, that is, F must divide P. Therefore, we can write P as Fg. Okay, we can write P as Fg. Is it clear? Is it clear? Okay. Okay. So, yeah, do not confuse this g with the gi's we had. This is some polynomial g. Okay. Now, so we have p is equals to fg. Therefore, what can we say about pt of gamma? So, pt of gamma is basically gt ft of gamma. Okay, both of these are polynomials in T, so they will obviously commute, right? So it's gt ft of gamma. Ft of gamma we had written as beta naught plus summation I equals to 1 to j gamma I beta I, right? So this is basically equals to gt of, this was beta naught plus summation I is equals to 1 to j ri of t beta I. Now we just write the jth term, or we just separate the jth term from this summation part. So we can write it. So it's basically so gt of rj bj beta j plus we have gt of beta naught plus we have summation over I is equals to 1 to j minus 1 now, right? Then we have gt rit beta I, correct? Okay. Now observe that this is an element from wj minus 1. Okay. Similarly, as we had said about something being an element from of wk minus 1, this part is an element of wj minus 1. This part is also an element from wj minus 1 because the subspace w naught is clearly in the sum of wj minus 1, right? From the left hand side, this part is also from Wj minus 1. Okay, that is Pt of gamma is also from Wj minus 1. That is exactly from the definition of P, because P is the T conductor of gamma into Wj minus 1. Therefore, Pt of gamma is, since Pt of gamma is in Wj minus 1 by definition of P, because P is the T conductor of gamma into Wj minus 1. Okay. Gt beta naught and summation over I is equals to 1 to j minus 1 gt rit beta I, both are in Wj minus 1 by the mere structure of j minus 1 or Wj minus 1 from step 1, because obviously we have chosen these vectors beta 1 to beta r such that they obey the property 1 and property 2 from step 1, right? So that immediately means that this must be an element of Wj minus 1, right? Therefore, Gt Rjt beta j must be an element of Wj minus 1. What is the T conductor of Wj minus 1? That's typically equals to, or rather should I say that what is the T conductor of beta j into Wj minus 1? Suppose that is Pj. Okay. What I'm trying to say is that, so if Pj is the T conductor of beta j into Wj minus 1, right, then Pj will obviously divide this polynomial. Then Pj will divide, this is also by definition of a T conductor. It's the generator, or let me not use the term, yeah, it will divide it as polynomial, right? G R J, right? Because the T conductor is basically the the generator of the ideal, which contains elements, which contains these polynomials. Okay. So Pj divides G of Rj. So this typically means degree of G of Rj. This is greater than equal to degree of Pj. But Pj is the T conductor of beta j into Wj minus 1, right? We will use the maximality property in the previous lecture. What can we say by the maximality property? By the maximality property, we can say that the T this will have degree greater than equal to P. Okay. So this will have degree greater than equal to degree of the T conductor of gamma into Wj minus 1, right? This was equal to degree of P, but P was written as degree of Fg, right? We are simply using the maximality property, that is point B from step 1. Okay, here. Clear? But if you quickly recall what was there in step 1, step 1 said that, sorry, this is step 2, let me come back to step 1. Yeah, step 1 said that if I have an index k between 1 and r, and wk is in this form, then if pk is the T conductor of beta k into wk minus 1, then this has the maximum degree of all the T conductors, right? So we simply use that factor. Okay. Yeah. So what does this mean? So this means degree of G Rj is greater than degree of Fj, right? Greater than equal to degree of Fj, but that means degree of Rj is greater than equal to degree of F, right? Therefore a contradiction, because degree of Rj by the division algorithm should be less than F, or should be less than F, otherwise Rj must be 0, right? A contradiction, therefore Rj should be 0, but we had chosen Rj to be obviously the maximum index that is non-zero. So right, we obviously reach a contradiction again, right? There is a contradiction, therefore Rj must be equal to 0, which implies Ri must be equal to 0 for all. Again a contradiction to the fact that J was the largest index such that Rj is non-zero. Again a contradiction. right? So we finally conclude the fact that uh, that Rj must be equal to 0. Must be equal to 0 for all I. Is it clear? So if Ri is equal to 0, then obviously that means that F divides Gi. Clear? F divides Gi for all. Now furthermore observe the structure we had got for the vector gamma. Yeah, gamma was like this. Each Ri comes out to be 0. Then Ft of gamma must be equal to beta naught, right? We had used the numbering 1 in the previous part. Let this be number 2, right? From 2, since each Ri is equal to 0, therefore Ft of gamma must be equal to beta naught. Therefore, by the T admissibility, by the T admissibility of W naught, there exists some gamma naught in W naught such that Ft of gamma is equals to Ft of gamma naught, but Ft of gamma is typically beta naught, so beta naught is equals to Ft of gamma naught, right? Okay, so we have finally proved step 2. What we do is that so we are left with 2 other steps. We are left with step 3 and step 4. In step 4 we will prove the uniqueness part, and in step 3 what we will do is basically we will be proving the cyclic decomposition theorem by showing that there exist vectors alpha 1, alpha 2 till alpha r such that the statement 1 and 2 of the cyclic decomposition theorem holds. And we will be simply using these vectors which we have constructed here in step 1 and step 2, which are beta 1 to beta r, and we will use the step 2 divisibility of f as well. Okay, so let this lecture be up to this much. uh, let's prove the cyclic decomposition theorem in the next lecture. So meet you guys in the next lecture.